Hello. Hello. Okay. Hello everyone. Good evening and welcome to the second tutorial of the course Nuclear Astrophysics. So today I will go through the your second assignments problems one by one, and if time permits I will briefly also go through the assignments from the problems from the assignment 1 also. Okay, I mean I will do all that problems. And before starting today's class I will just correct one mistake which I did in the previous class. So while I was calculating the parallax method, so this figure you can see in my last class. So there a mistake I have done in this part. So while focusing on this particular triangle where this is the 90-degree angle and this is the alpha angle, so tan alpha actually will be the base, which is this one. So the base is actually, this is the base of that triangle, which is 1 AU distance between earth and sun, and then the base. So for our case the base is this d. So instead in the last class I write it tan alpha equals to d by 1 AU, which was actually incorrect. So the correct expression will be this one, tan alpha equals to 1 AU by d, and all the other things are same, that for very small alpha, tan alpha can be approximated as alpha. So alpha equals to 1 AU by d. So instead alpha d by 1 AU, the correct expression will be alpha equals to 1 AU by d. Okay, so that was the mistake which I found later. So please, if when you are going through that first class, just correct this part. Okay. So I will erase it and we'll start today's class. Okay, so today I will go through that questions as I told you in the assignment. But before starting directly to the before coming to directly to the assignments, I will just tell you about something which I have found that sir have covered in the class, but I will give you a brief overview of that. That is the absolute magnitude and apparent magnitude. So when you are coming when you are going through that HR diagram, you can see that in the y-axis it has been plotted as a function of the y-axis is absolute magnitude, and here this is luminosity. So that's why I thought I will give you the idea of the absolute magnitude and the apparent magnitude first, then I will come to this HR diagram and we will do all the problems one by one. Okay, so actually the magnitude is a system to identify the brightness of a star. So this is the measurement of a brightness, you can say. Like in the last class I told you that let me use blue, yeah, the luminosity of any star is 4 pi r star square sigma t to the power 4. Okay, so that was the luminosity. Now suppose this is a star. So this star has a luminosity 4 pi r square sigma t to the power 4 r star, whatever. Now this light or this photon, that will travel every direction from the star, right? It will travel in any direction. And now if you consider a surface like this around the star while the star is at the center of the circle, then the luminosity which is coming out from the star L, that will go through all the will go through this total surface, right? This total surface which I just draw, this total surface, I mean how much energy is coming out of the star, it will go through the total surface, the big surface which I have drawn. So if the distance is capital D, then the flux which is measured at a unit surface at that distance at D, that will be that L which is coming out from the center divided by the total surface area of the sphere. which is 4 pi d square, right. So this is actually the flux which can be measured by sitting at this particular place. Now suppose this place it is the earth, okay. So this is the earth and this is the sun. Suppose where the earth is at a distance of d from the sun, so the observer who is measuring the flux of the star by sitting at this exact position, it will get the flux as L by 4 pi d square, okay, where L is the luminosity of sun and d is the distance to the sun, distance of the sun from the earth. So this is how flux is can be expressed mathematically. So this is F. Now the magnitude system, it is related to the flux actually, which is measured at the position of the earth, okay. So this magnitude can be expressed as, it is just a system, everything is related to the brightness, while I am talking about flux or the magnitude, just a system of expressing. So magnitude M is minus, just remember this formula, 2.5 log 10, I mean log base 10 F, okay. So this is, and there will be a constant, so don't bother about this constant, this is some factor which comes due to the measuring instrument. Just focus on this part, that minus 2.5 log F, where this F is similar, I mean same as this F, that means this F is the flux, okay. Now so as I write, as I have written that expression of that F is 4 pi d square. So please just I mean my square notation is not good, so when I am writing like this, just consider it as square. I am writing square, I will try to improve it, okay. So L by 4 pi d square. Now this is the apparent magnitude. So why it is apparent? Because you can see that if suppose you have a star which is at a distance L, which is at a distance d having luminosity L, for that case this is the flux. Now suppose you have another star which have a luminosity of 4 times of the luminosity as previous, that means 4L, and the distance is suppose double of the previous distance, that means d has become 2d. So this will be the flux for this star. Now if you write it, it will be 4 pi d square times 4, and this 4 cancel out. So you can see that here you are getting L by 4 pi d square, here also you are getting L by 4 d square, but you are measuring the same flux, but the distance and the luminosity has been changed, where in this second case the distance has been doubled from the previous and the luminosity has been 4 times from the previous, but we are getting the same flux. So from the apparent magnitude you cannot tell clearly which star is brighter or which star is fainter, because there is a degeneracy between luminosity and the distance, and that can accommodate themselves in a way that you may get same flux from 2 different stars, okay, that I have shown you. So that's why this absolute magnitude comes into the theory or into the literature, so that from that absolute magnitude we can clearly tell which star is fainter or which star is brighter, which cannot be said by the apparent magnitude. So what we have done in the for the absolute case, nothing, we just fix the distance here, like capital M, that is the absolute magnitude, it is same as previous case. So in the previous apparent magnitude it was the distance, now the distance has been used as 10 parsec, that means it is the flux if the star located at a distance of 10 parsec instead of any arbitrary distance, okay. So that's why it is called the absolute magnitude. Now you can see as the now your distance is fixed, so that means if your L increases, that means your M increases. M increases, I am saying the modular value of M, okay, although there is a minus in front of that value, that means it is going to the greater negative, but I am telling about the magnitude value. So L positive means mod M value is going to a positive direction, or you can say M which is taking account into the negative sign, that is going lower and lower. So here, from here we can clearly say by comparing two absolute magnitude value of two star, which one is brighter and which one is fainter, because the degeneracy of the distance that is gone in this absolute magnitude scale. That's why this absolute magnitude is important, and it is a good parameter to compare the brightness between different stars. Okay, so that was the main point. Now small m and capital M I have written. Now there is you can calculate also small m minus capital M, that is minus 2.5 log. Now that will be L by 4 pi 10 square into 4 pi d square by L. Just a log a minus log b equals to log a by b, that I have done here, and it will give you let me check. Yeah, there will be plus, because I am dividing the absolute magnitude, so the minus will come, minus of minus will come become positive. So 2.5, this is a simple mathematics, you can do it by yourself. It will be d by 10 square. Okay, so this is called the I mean difference between the apparent magnitude and the absolute magnitude, and that can be expressed by 2.5 log d by 10 square. So this square can come in front of that log also, so d by 10. Okay, so this is the expression. Now if you know the difference between, I mean if you know the apparent magnitude and absolute magnitude of a star, from this expression you can find what is the distance of the star, and vice versa. I mean if any of the two unknown is known to you, then you can calculate the other. Okay, so this is a very important formula. M minus small m minus capital M equals to 5 log with the base 10 d by 10. Sorry, what happened? Something happened. Sorry. How to do it full screen? Okay. So yes, sorry for that. So this was the thing what I wanted to tell you, and if time permits, at the last of today's class, I will do some more interesting facts about this absolute and apparent magnitude. Okay, so right now I will not do it. I will do it if time permits at the end. Okay, so this was the apparent brightness and apparent magnitude and absolute magnitude. Now I am coming to that HR diagram. So now you can understood the absolute magnitude. Higher absolute magnitude means higher luminosity, and lower absolute magnitude means lower luminosity. Okay, so let me calculate interestingly. So in the class you have seen that sir has already calculated what would be the possible radius of supergiants by this by following this HR diagram, and he asked you, I mean the students, to do it for the lower level stars, that means the white dwarfs. So I will do one thing. I will calculate this lower left hand, this part, by following the same method for white dwarfs. Okay, and I will particularly focus on Sirius B. So from the HR diagram I have the temperature, the luminosity, and from that I will calculate what could be the possible radius of Sirius B by using the values of HR diagram only. Okay, so and I have particularly considered this Sirius B because the value of the exact value of Sirius B is available in internet, and we can compare our calculation after the we can compare our calculation with the available result while we are how much close we are. Okay, so that we will do. Okay, so now coming to this point, the Sirius B. So you can see it is a white dwarf. It is in the left. It is in the lower left part of the HR diagram. Now the luminosity is roughly this line is 10 to the power 3 luminosity 30,000 sorry So the temperature is just above 30,000 degrees. So I will take rough estimation, it is 30,000 degree Kelvin. That is coming purely from the HR diagram only. This value, this 30,000 value I have taken, and the luminosity, which is this axis, the luminosity is slightly above, although it is not a straight line, still assume it is slightly above 10 to the power minus 3, okay, of solar luminosity. So I will take that the luminosity is slightly 3 times 10 to the power minus 3 of solar luminosity. Okay. So how to Priya I have asked how to register in the exam. So that I actually don't know how to register. I will try to find it out and will let you know. Okay. Okay. So coming to this part. So from the plot we have taken two rough values. These are estimates, not exact values. Estimates from HR diagram for series B. Okay. Okay. Now as I told you that L is equals to 4 pi r star square sigma t to the power 4 luminosity, valid for any star luminosity. Now L by L sun, that is r star by r sun square time t star by t sun to the power 4, right? It is actually coming from here. 4 pi r star square sigma t 4, let us put is t star, no problem, t star, and the L luminosity of star will be 4 pi r sun square sigma t sun to the power 4, that is here. Now L by L luminosity is coming from here, that is 3 into 10 to the power minus 3, okay. And this we will calculate r star by r solar square time t star by t sun. So t star here I have approximately taken it at 30,000 Kelvin, and for sun the temperature is actually 5,800. Okay, so for the for simplicity we will take it as 6,000 roughly. So T sun roughly 6,000 Kelvin to the power 4. Okay, so this will give you 5 roughly. Now that means your r star by r sun square is 3 into 10 to the power minus 3 divided by 5 into 5 to the power 4, right? And if you remove that square, it will be 1 by 2 of the right hand side. Okay. Now if you calculate, this will give you a value of nearly 0.003. 0.003. Okay. So we have calculated approximate radius of a white dwarf Sirius B by following only the HR diagram, that it is nearly 0.003 times of the R sun. Okay. That means there is a option. Okay. So 003. Now this we have got from purely HR diagram. Now what is the actual value? We have to compare with the actual value so that we know that yes, we are doing something which is close to the realistic answer. So for you can find it in the internet. I have written down just a thing. Yes. So R Sirius B by R sun. This value I am writing from the internet. So it is approximately 5,500 kilometer. You can see it. You can find it in the internet, and it is approximate value. And at it you know that it is 7 lakh kilometer. Right. So now this will give you a value of 0.007. So this is real value and this is our estimation. So you can see that we are not very deviated from the real value. We are just getting a lower factor, I mean, we are getting a lower value which is deviated by a factor of 2 only, 2 or 2.5 only, you can say. So approximately we are getting a close value to the realistic scenario. So this is the usefulness of HR diagram. From the from the position of the star in the HR diagram and calculating the approximate flux and the approximate temperature, you can find a approximate radius what could be for that particular object that we have done. So you may think that 0.003 and 0.007, that is a big difference, but in astronomical scale this difference is very minute. So this is a very small difference, and you can, I mean, we are this result is agreeing the realistic scenario, which is 0.007. Okay, so that we have done in the HR diagram. So till now, anyone have any question? Okay. Okay, so the similar thing sir have also done in his class. He have calculated the radius of the supergiants from the HR diagram, and it was some 100 times larger than the sun. It may go to very high also. I mean 500 to 200 to 500 times suns. That is also possible. So this is all our approximations. Okay, so this was an interesting thing which I wanted to share with you, and comparison with the realistic case. Now coming to directly to the problem of the assignment. So you can see that the first question was that the velocity distribution of the particles in the stellar plasma has a maximum at which temperature, at which velocity. Okay, so this is a black body radiation. I mean black body radiation spectra, which is same like stellar spectra. I have shown in the first class the stellar spectra closely follows this black body type spectra, and this highest temperature, this we can calculate by the Wien's law, the famous Wien's law. Please I don't remember the exact what is the name. It may be WINE, so just check it with the book. So that tells you that lambda mt is constant. This is the famous Wien's law. Okay, and from there you can calculate what is the t. T can be calculated. Okay, so you have the value of t at the peak of the distribution, and you can see that this peak follows the most probable speed of the distribution. That means the particle which has speed which is, the particle with most probable speed will be at that peak of the spectra. Okay, so that means the kinetic energy half mv square will be equals to the E thermal, which is the thermal energy, and at the peak if the temperature is T, then the thermal energy will be K times T, where K or Kb, I am writing it as Kb is the Boltzmann constant. Okay. Boltzmann constant. So actually, so this T, it is calculated from the lambda mt indirectly from the spectra itself, and the energy at that particular T is kBt, and if you calculate that kBt with the half mv square, which is the kinetic energy of the particle, that will give you the most probable velocity. It mainly comes from the velocity distribution of Maxwell-Boltzmann type velocity distribution. Okay, so here your v square is 2 kBt by m, that means v equals to 2 kBt by m root over. So that is your answer. It is the most probable velocity. So there are other things also, like the average speed, which is different from the most probable speed, and the root mean square speed. This also you can calculate using the distribution which is shown in the figure. So that this is the Maxwell-Boltzmann distribution. I mean, I have used this figure as the black body spectrum, but actually it is not black body spectrum. Black body spectrum is closely follows like this, where f and lambda. As this figure follows the same type, that's why I told you this is T, but don't confuse it with the Maxwell-Boltzmann distribution. It is actually T. Okay. I have just used the spectra because the shape of the black body radiation and the Maxwell Boltzmann distribution are same. That's why I have used that thing. So this is actually the black body spectra. Okay. So that T we calculate from the peak lambda mt, and then we equate that thermal energy with the kinetic energy of the particle, which will give you the most probable velocity. So this will be the answer, 2 kBT by m. Okay, now coming to the second question, it was this I have done, I mean roughly I have done in the previous class also. If you go through, you can find it that I have done it, but I will again do. Okay, so yeah, so here we have to calculate what is the thermal energy at the sun's core. That means in this region, this is the core of the sun. The temperature of the core is not similar as the temperature at the shell. The shell temperature may be very less. You can see the shell temperature, which is only 6000 kilometer at the surface of the star, but at the core the temperature is 20 million degree Kelvin. Okay, so whenever you are going deep into a star, the temperature will increase. So never confuse that while calculating the luminosity, I have used the temperature at 6000 Kelvin. Here you can see that here I have used the temperature of 6000 Kelvin, which is same as this, but at the core the temperature is quite different from the 6000 Kelvin. Okay. So that we will calculate that. So the T core is given as 15 million Kelvin. Here it is 20 million Kelvin, but in question it is given 15 million Kelvin, no problem. And we will calculate the thermal energy E thermal, which is actually kBT. Okay, kBT, kB is the Boltzmann constant again. So that so value of kBT is actually 1.38 into 10 to the power minus 23 meter square kg second to the power minus 2 Kelvin inverse. I think it is right, yes, times the temperature, which is 15 million Kelvin. That means 15 times 10 to the power 6 Kelvin, right? Okay. Now this is in CGS unit. Okay, but here you can see it is in electron volt unit. So in astronomy or astrophysics, the we use mega electron volt more than the typical CGS unit, which is joule, CGS or SI, joule or arg. Instead of joule or arg, we use generally electron volt unit for the measurement of energy. So I will write this kB Boltzmann constant in that electron volt unit, and just you can convert it by it yourself, that it will come 8.617 into 10 to the power minus 5 electron volt K inverse. Okay, and 15 10 to the power 6 K. So this value and this value is just differing because I am using a different system of measuring. It is in electron volt unit, where it was in the CGS unit or SI unit. It is a meter square kg, that means it was in SI unit. So but always go to the electron volt unit while you are calculating anything for the astrophysical scenario. So that will give you a value of 129.3 times 10 to the power minus 5 times 10 to the power 6 eV, which is 1293 electron volt. Okay. And if you convert it into kilo electron volt, that means 1 keV is actually 10 cube eV. So you have to divide it by 10 cube, and it will give you 1.293 kilo electron volt. Roughly what you can write as 1.3 kilo electron volt. Okay, so 1.3 kilo electron volt. This is the answer. Now I have also done it roughly in the previous class. You can see there I have calculated the thermal as roughly 10 to the power minus 3 mega electron volt. That means roughly 1 kilo electron volt. That was not so accurate. That's why we have got the 1 kilo electron volt. Instead you are getting 1.3 kilo electron volt, quite similar. Okay, so this is the main thing. Now okay, so 10, yes. Now I will go to the question number 3. Yeah, here it was an interesting question. The star with mass 10 times that of sun. I mean up to here, there is there any question? Okay, then coming to question 3, that a star with mass 10 times that of a sun consumes its nuclear fuel faster by what factor? This also can be done if you have closely, if you had closely follow my previous video. There I have also calculated, a lifetime of a sun. I mean, what will be the life duration of a sun if it at the rate which it is going right now for the thermonuclear reaction. I mean, the rate of the thermonuclear reaction divided by the luminosity, that will give you the lifetime. So that exactly same thing we will do here. We will calculate the tau of that star. Okay. So tau means the lifetime. Okay. So for sun, if you go to the previous lecture, previous video, you can see I have used this particular formula. Sorry, arc by gram divided by luminosity of sun. Okay, so here this is x. Okay, this is x. This is multiplication. So that is qxm times 6 into 10 to the power 18 arc per gram by the luminosity of the sun. That will give you the lifetime of a sun. So that means your lifetime of any star, not only for sun, it is proportional to the mass of the star. It is mass. Okay. So lifetime of a star is proportional to the mass of the star. Okay. Now, and here there was a luminosity of the star. Okay. Now, if you can express your luminosity by the mass, then you can calculate what will be the lifetime of the star depending only of the mass. Okay. So if I can write L, this L as a function of L m, then suppose m alpha, and the numerator have one m itself, so that will be m to the power 1 minus alpha. It is very it is a useful thing if you can express our Lm in terms of m to the power something. Okay, so that's there it is coming, the famous ML relation or the mass luminosity relation of any star. So here you can see that generally this is a diagram of luminosity, and here the distribution of stars are there. So roughly this follows, this luminosity mass relation follows L varies m to the power 4 roughly, because it is not any theoretical value, it is coming from purely observational. So this m to the power 4 is coming from fitting the data with your known graph plot, I will say. So if you follow this, L varies m to the power 4, that means your T star will be m by m to the power 4, that means m to the power minus 3, right? All other factors will be there, that's why I am writing it as a proportional factor. But if you compare it with the sun, T star, just a second, yeah, sun, that will be m star minus q by m sun minus q, right? All the proportional terms will be cancelled out. Now, in your question, it is given that a star with mass 10 times of that of sun, that means m star by m sun is equals to 10. If we put it here, 10 to the power minus 3, that is 1 by 10,000, right? Okay. So we have calculated the lifetime, that if the star, this star has mass which is 10 times mass of the sun, then it has a lifetime which is 1000, which is which is less than by 1000 factor by the sun. Okay. So T star by T sun, T star by T sun is equals to 1 by 1000, that means T star is less than T sun, although m star is greater than m sun, right? That means your heavier mass star will have lower lifetime, and similarly your low mass stars has higher lifetime. Now your question tells that a star with mass 10 times that of Sun consumes its nuclear fuel faster by what factor? So, what is, sir, can you share today's class YouTube video? Yeah, I will share after the class. It will take 1 to 2 hours, and then I will share it. So you can find the previous lecture also, previous class also in YouTube. So I don't know how the actually PMRF NPTEL authority works. If had they shared any link with you, of my first class, so please let me know that. Yeah, if any okay, they have not shared you, so I don't know. Just a second, I will type here the link of that class, just copy it. Okay, just a second. So this is the link of the first class. Yeah, so you can find it here. Okay. 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 Anyone have any question? They can ask also instead of writing, no problem. Okay, now coming to that part. So as I was telling that your lifetime is lower, that means a star's lifetime is lower, that means it is burning its fuel in a higher rate. Okay, so actually that means the burning rate will be 1 by proportional with the lifetime. Okay. So we have calculated the lifetime will be 1 by 1000 time. That means the burning rate for this sun will be 1000 times that of the burning time of the star will be 1000 times that of the sun. Okay, because it is the reason why the lifetime is lower, because of a higher rate of burning. So remember this, that burning rate is 1 by lifetime. That's why I am getting 1000 times of burning rate, which is asked in the question. If it has been asked that what will be lifetime of the star, lifetime of the star with respect to sun, then our answer would be 1 by 1000 times. But as it is asking about the burning times, how the nuclear fuel faster burn, that means burning time, that will be 1000 times. Okay. Okay, now I will briefly give you a small idea. So you have seen that in the lecture, sir has also told that L is varies m to the power 3 by 5. Here I am using m to the power 4. So all these are empirical. There is we still now we have not proved anything by the theory, but I will try to give you some idea from where it is coming, that L is proportional to m to the power some power. So here as I have written here. So for this problem I found that m to the power 4 has to be assumed, so that you get an answer. So please remember that it is not there is no hard and fast rule for that. Like here you can see it is a mass in solar masses and luminosity. This is a mass luminosity relation taken from internet, and you can see that here they are using 3.5 instead of 4. So this parameter is variable and people use different values because there is no hard and fast or solid theory to prove it. It is coming from the fitting of the data. So fitting of this data, this type of thing. For the low mass star it will fit it like this, then it will change its slope, then again it can change slope. It is not a one slope thing. That's why you can see that for very small star which has mass less than 0.43, it is going as 2.3 the factor, and if it is between 0.43 solar mass to 2 solar mass, it is going as 4, which has been taken in this particular problem. And if it is greater than 2 solar mass and less than 55 solar mass, it is 3.5. And if it is very high mass, that is greater than 55 solar mass, then it is 1 actually. Okay, so you can see that this index is not fixed. It varies depending on the mass range. What happens? Someone was trying to present. I don't know why. Just a second. So Satya Suji is trying to present something, so I think he have done it by mistake. Okay. Yeah, can you see it? I think you can see it now. Okay, so as I was telling that this value is not constant and we will use different value. Now for very I mean what I will be telling in the next 7 to 10 minutes, you don't have to understand it, I mean in very deep. I will just try to give you an idea about how these values are coming from a theoretical background, very small, no, okay, just 5 to 7 minutes maximum. So basics of this ML relation from the theory. What actually I think you will come to this part which I am writing right now. So a star evolution, that will depend mainly on 4 equation. Okay, just try to see it. I think if you don't understand it is okay, no problem. That is Gm rho by r square. It is called the hydrodynamic equilibrium. Just follow me. Okay. You don't have to derive, you don't have to understand if you don't want, no problem. Dm, I will not write, dm by dr, this p is the pressure of the star, this m is the mass of the star at a distance r, that is 4 pi r square rho r. Okay, this is coming from the mass conservation. Okay, then dl dr, where L is the luminosity of the star, that is 4 pi r square rho r epsilon r. So epsilon is the energy, creation of energy, which is the thermonuclear energy, that is, and this L is the luminosity. This is called the radiance equation, and there is another one, that is dt by r, that is T is the temperature of the star. Okay, that is 3L k rho by 4 pi r square 4 AC T r cube. You don't have to understand any of this thing, nothing. So this L is the luminosity only, this K is kappa actually, that is opacity, and rho is the density. So which you have to understand, that is this P is the pressure of the star, M is the mass, rho is the density. Okay, here also M is the mass, rho is the density, L is the luminosity, rho density, epsilon denotes the generation of thermonuclear energy, nuclear energy. Here this is also density, luminosity, and T is the temperature. I mean this P, rho, L, T, all the properties of this star is interrelated with these 4 equations, and from here you can get a rough idea of the mass luminosity relation where I have told you. So let me use it. So focus on this particular equation, which was the hydrodynamic equilibrium equation. From that equation we can write P is proportional to rho m by r, right? Rho m by r. Why r? Because if you integrate dp dr over r, then this r square will give you a r in the denominator. That's why it is not r square, it is r, because it has been integrated over the dr. Similarly, this particular equation will give you just this called the scaling relation of astrophysics. So this is very important if you want to pursue astrophysics in future. So this is called the scaling relation. Where here you can see this rho and r square, it will be integrated over r and it will give r cube, right? Rho r cube. And this one, this temperature equation, that will give you L in terms of T to the power 4 r by kappa rho. Don't bother about this kappa, this is a constant, that is opacity. So I have just written this L in terms of T. Just I have shifted the left hand to right hand. So this scales relation is coming from the all the equation which is governing the evolution of a star. Now another thing, you know that your pressure, a star is made of gas particle, roughly, or plasma particle, what you can say. That follows the pressure is nkt. This is the obvious gas law, P equals to nkt, PV equals to nkt. That's why I have not written the V, that's proportional. And this n means number density, and this k is the constant. Now if we don't write the k, we can write it as rho t. Okay, rho t, because the number density is proportional to rho, the density of the star. P equals to rho t, and here it is given already, that is also equals to m rho by r, right? I have just used this. Though, so this rho and rho will be cancelled out, and t will be scaled as m by r. Is it clear? From this only. So P is m rho by r, that is coming from the hydrostatic equilibrium, and also we know that P is equals to nkt, that means P is equals to rho t. So by equating that two, we are getting T, the temperature of the star, is scales as m by r, which is interesting. Now what we will do, we will just use this fact that temperature is proportional to m by r in this another equation which is there, that is L. Not equation, scaling relation I will tell. So L will be T to the power 4 means m by r to the power 4 times, there is r, forget about that kappa k, that is constant, and rho, right? This rho. Okay, so this rho can be also written as rho varies m by r cube. Actually I am trying to go to m and r from all the other quantities. So this equation tells you that rho is actually m by r cube, right? This one tells you rho is actually m by r cube, and if I put it here, m r cube, so you can see r cube and r will make it r to the power 4, which will cancel it out, and it will be L varies m cube. Okay. So this is the approximate result of the mass luminosity relation of this particular relation from just the scaling mass luminosity relation from just the scaling argument of the evolution of the star. Okay, so you can see we have found 3. So this 3 is not much bad in the range of 3.5, 4, 2.31. So this 3 is a good result. We can say that roughly we are only from using the scaling relation we are getting something which can tell how the L and M are related. Okay, so this is just a rough form, not exact, but I tried to give you some idea about how this mass luminosity relation comes into the picture. Okay, so remember that L varies as like this for different range. Roughly you can do your math using 3.5 or 4, whatever, and from theory we are getting 3, which is close to 3.5. Okay. Okay, so that was an interesting thing. If you don't understand, just go through the recorded video again, you will just understand. It is nothing but does this 3 use, I mean very simplified relation for P, M and R here, this one. Okay, so now I will come to that question 4. It is very easy, that calculation of Q value. If you have any question, you can ask anytime. Okay, so you know that how to calculate the Q value. Let me go to blue again. So Q value is actually the total mass of the reactant minus the total mass of the product and times C square. That is actually delta m C square. Okay, so delta m is the mass of reactant minus mass of product. So we will do that. M of mass of 3He plus mass of 3He, because 2 3He is there, minus mass of 4He minus 2 mass of protons. Okay, 2 protons are there, times c square. Now we will do it in the MEV unit. So that's why all the values of this mass we will put it AMU unit, and 1 AMU will give you 931.5 MeV of energy. This you know, I think, everyone. So that's why we don't go through the longer process that writing AM, then again c square, then again converting it to energy. I am just writing it as 931 AMU will give you 931.5 MeV energy. Now if you put all the values which are given, just it is a value putting problem. 3.016, 3.016, 4.0026 minus 2 times 1.00727, okay, times 931.5 MeV. These are all in AMU unit, as we are multiplying with 931.5. You can do it in kg, in by putting the c square, calculate it in joule, then you can convert it MeV also, but this is the easiest process now. So it is 0.01486 times 931.5 MeV, that will 13.842 MeV. So this is the Q value, 13.8 MeV, okay, for this reaction. Now I will do one thing which sir have asked you to do, but I don't know whether you have done it or not. That is the Q value of beta decay. This is a very easy thing, I think everyone can understand. Now, yes, any question? Okay. Now I will go to the Q value of beta decay. So there is two types of beta decay. One is beta minus decay and one is beta plus decay. So I will do for both of them. Beta minus decay is actually a particle X with Z and A. Z is the proton number, A is the mass number, will be decay like this, and there will be a electron. Minus 1 E, 0 is the electron. And beta plus decay is just the opposite of this, that is Z A, Z minus 1, Y A, plus 1 is 0. So this is positron. Plus 1 is 0 is positron, which is same as electron with a positive charge equivalent to the electron. And now an example of it is a neutron decay. 1 P1 plus minus 1 is 0. This is an example of the beta minus decay. Similarly, a proton decay is an example of beta plus decay, proton to neutron. That is plus 1 E 0, and so let me plot it with that. And there will be a electron neutrino. Okay, so these are the two very simplest example of beta plus decay and beta minus decay. So beta minus decay is actually a release of an electron, and beta plus is actually a release of an positron. Okay, so as positron has positive energy, that's why it is called beta plus, and electron has negative energy, so it is beta minus. Okay, so we will calculate the Q value of beta minus. So that will be mass of nucleus of this X element, which has a proton number of Z and mass number of A, minus mass of nucleus of Y, which has a mass number of A and Z plus 1 proton number, minus mass of the electron times c square. This should be the beta Q value of this particular reaction. Now this is the mass of the nucleus. We will convert it as a mass of the total atom minus mass of the electron. Okay. So that means actually MnAz, it is the mass of nucleus. So it is mass of nucleus plus Z of Me, this is mass of electrons, that will give you the total mass, that is Az. Okay. So just focus that here I have, that's why I have written the small n in the subscript to tell you that it is the nuclear mass only, not the whole mass. So nuclear mass plus mass of electron, that is the total mass. Okay, that means m of Az minus Zme, that is mn of Az. Okay, that we will do that mn Az, we will write it m of Az minus Zme. Similarly, it we will write it m of Az plus 1 minus of minus, that will be plus, just subtracting the mass of the electrons, Me minus Me c square. Okay, so this is the thing, and if you do all the like this plus Me will cancel out this minus Me. So if you do all that cancellation, it will be, just do it, m of, and this Zme, it will cancel this Zme. Okay, so this Zme will be cancelled out by this thing, and this minus Me will be cancelled out by this thing. Okay, so Z plus 1 c square. So it is the Q value of the beta minus decay. Now here it is the total mass, that means the atomic mass, total mass of X Az, and this is the total mass of Y, sorry, Z will be Z plus 1 A. Okay. So this is how you can express the Q value. Now another interesting thing, you can say that if the mass of X is greater than the mass of Y, then your Q beta will be positive. That means it will release energy. That means if the particle which has been created by the nuclear reaction, that is Y, this one, if it has a mass which is less than the parent particle X, then it will release energy. Exactly what happens in fusion, that two smaller nuclei will sorry, it cannot be compared with the fusion, it is actually fission. So in fission, two small nuclei will create a high mass nuclei, and some energy will be released. Oh, just a second. Okay, so that is my mistake. I generally confuse between fission and fusion. So M parent is greater than, that means it is fission. So high mass particle is making two small mass particle, right? That's why the daughter particles have lower mass, and it will release some energy. What I told in the previous case is not correct, that is wrong. So I have some confusion between this fission and fusion. Okay, so sorry for that. Now this is the important thing. Now we will do it the same thing for the beta minus decay. So Q of beta plus decay, sorry, that is M nuclear mass of Az minus nuclear mass of Az minus 1 minus Me c square. We will not consider the mass of the neutrino because it is a very light particle, and we generally don't consider the neutrino mass. Okay. And if you, similar way, if you convert it, the nuclear mass to the atomic mass, it will be M of Az minus Zme minus M of A Z minus 1 plus Z minus 1 Me. Okay, so one thing I have mistaken it. So M I have written in small, mass of electron small, Me minus Me times c square. Okay. Similarly, if you calculate, you will get M Az minus M A Z minus 1 minus 2 Me c square. So this is the beta, this is the Q value for your beta plus decay. Right. So this was the beta minus decay, this was the beta plus decay. Here it was the difference between parent element and the daughter element. Here it is the difference between parent, daughter, and extra mass of 2 electrons is coming into the picture, that is minus 2 Me. So this is the difference in the Q value of beta plus decay and beta minus decay. So I think you have if you have any problem, you can say. Okay, now coming to the next problem, I think here I have marked the answer, yes, 13.8. Now coming to the next question, all the other questions are I think mainly theoretical. One there is a mathematical, okay, no problem. So which of this is unstable? So diproton, neutron and dineutron. So I have found some images from the internet. So this is the diproton. This diprotons mainly decays into 2 protons. Okay, so diprotons is unstable, right? Normally here it decays by either fission or proton emission, but 1 out of every 10 to the power 9 diproton beta decays to deuterium. So it can be decays into deuterium or protons, but the main point is it will decay. And second, the neutron. So this is the neutron, and I have shown here also that this is the neutron decay, which is actually the beta minus decay. So neutron will also decay, that will create a proton and one electron, and similarly one electron antineutrino. So yes, so here also I should have written an electron antineutrino. Okay, but that will not affect the I mean that neutrino will not affect the Q value calculation. Okay. So neutron also will decay, and dineutron. So dineutron is actually a intermediate part, you can say. When a silicon atom decays, it will go through a phase where a dineutron atom, I mean where a dineutron like structure is formed. This is the dineutron. 2 neutron is, you can say, you can consider is added. So that is called the dineutron, and then dineutron will also decay into 2 neutrons. So dineutron will also decay, and the main answer is all of them will decay. So these are the 3 figures which I found for these 3 elements which will decay. Now here it is also written that you can see that it decays through a process called the neutron beta decay, which I have done for the beta decay Q value calculation, transmitting an electron and an antineutrino and protons. So all these 3 elements will be decayed. So the right answer will be this. Now 6, find the luminosity. So this is very easy. Just I will put the values. I have yeah. So many times I have told you that L is 4 pi r star square sigma t to the power 4. Here all the values are given. This is the r star value, it is the t value, and this sigma you already know. So that will be 4 pi 696,340 kimi. So I will convert it into centimeter. 10 to the power 5. I also forgot what is the centimeter conversion. Then 5.67 into 10 to the power minus 5. It is the value of sigma. Okay, it is the value of sigma. It is it is, yes, and there will be the unit will be, just go through the book if I am doing anything wrong. I also forgot. Might be this is the unit of the sigma, and your t is 5778. It is written k to the power 4. I think it is right, because this k to the power 4 will be cancelled out by this k to the power 4, and all the other things will be cancelled out, because this centimeter square will cancel this centimeter square, and the total unit will be arc per second, or arc second inverse, which is correct for luminosity. I think those are correct. So if you calculate, it will be 3.85 times 10 to the power 33 arc per second. Okay. This is, and actually the solar luminosity is 3.84 times 10 to the power 33, the measured solar luminosity. So you can see this is similar to this, because this radius is actually the sun's radius, 7 lakh kilometer approximate, and I told you that sun's temperature is 5800 Kelvin. So actually this problem is this star is actually sun. That's why you are getting a value of same luminosity of a sun. So this was the 3.85 10 to the power 33. This one I think right answer. Okay, so 6 is done. Now 7. Okay, 7 is, which of the following process is responsible for the projection of elements having mass number a? This is directly asked from the video, I mean lectures. So, but I have used a picture so that you can remember, because pictorial representation is easier to remember. Okay. So, here you can see this type of structure I have discussed in the previous class also, that there will be different zones of nuclear burning. The central zone will be the higher element, and as you go out from the center, the lower and lower element will be burning. So, here you can see it is the lowest element. Lower and lowest I am telling in respect of the proton mass number, okay, and this is the highest, this is the Fe, iron. And you can see that carbon burning process will give you neon, neon burning will give you oxygen, and then oxygen will fuse into silicon, and after silicon has been formed, then that silicon will go through different type of reactions. So, here silicon will helium, that will give you sulfur, then that will give you chromium. I mean, all the other elements you can find here, I will not go through one by one. So, here you can see just one thing, notice that mass number, it is 32, it is 44, 36, 52, 40 and 56. So, all the mass numbers are between 32 and 56. That means, which is given in this question, that from 28 to 60. These elements are mainly forming from the silicon burning process. Okay, so this is the silicon burning process. Just this much is to be discussed for this particular question, nothing much. So, silicon burning process. Carbon burning will give you neon, this. Oxygen burning will give you silicon itself, okay, and neon burning will give you oxygen. Okay. So, this was the, and SRP process, these are for higher elements greater than 60. So, A greater than 60, this dominates the SR and P process. I process, actually I also forgot, I have to go through this particular process, but these are not silicon, I mean for 28 to 60. Okay. So, just try to remember this figure, how the elemental, I mean burning happens inside a star. It is like a cell type structure. Now, one question, what is the anticipated future of a sun? Okay, so these are the theoretical questions, that's why I have put some theoretical writings which I have found in the internet. So, I will tell you that there is, the life cycle of stars actually depend on the mass of the star. I mean, if the mass, I mean, here you can see there is two life cycles. So, this was the planetary nebula, which is the birthplace of a star. Then it is the average star, I don't know whether you can see it or not, and it is a massive star. Massive stars mean greater than 8 to 10 times of solar mass, and average star means a solar mass star. So, if the mass has a, if the star has a solar mass or the average mass, then it will go through this phase, which is the red giant phase, then it will be a planetary nebula, and then it will end its life as a white dwarf. Okay. And if the mass is very high, greater than 8 to 10 solar mass, then it will be go through red supergiant, then there will be supernova explosion, and then neutron star or the black hole can be formed. I cannot tell you in details what those objects are, because that will take much time and it is not covered in this particular course. So, massive star means it can go to black hole, and low mass star, low mass sun-like star, low mass means sun-like star, those will go to a white dwarf, okay. So, it is, I mean, that's the theoretical back point of answering the question. So, it will, sun will become a red giant during the helium burning phase, it will be the answer, because here you can see the red giant, and the final phase of the life cycle will be dwarf star. So, for this question it will be sun will become a red giant during the helium burning phase, which is this particular phase. Okay. And sun will ultimately collapse into a black hole. It is not possible, as I told you, the mass is very low. It is impossible to predict the future of sun. It is not possible, it is possible, and it has been predicted for many other stars also, correctly predicted. And energy production will stop after hydrogen burning, as the sun is not massive enough to burn helium. No, it is not also correct, because the sun is enough massive to burn helium at least. Okay, so this is the answer. This is the answer. Okay, now this is taken from the NASA website. This line I will just read it. Like most stars, during the main phase of its lifetime, the sun creates energy by fusing hydrogen atoms in its core. In about 5 billion years, the sun will start to run out of hydrogen in its core to fuse, and it will begin to collapse. So, if there is no nuclear energy or the thermal energy to balance the gravitational contraction, it will collapse. So, that is why it began to collapse, and this will let the sun start to fuse. I mean, that collapse means the temperature will increase, and increased temperature means the higher element will be burned. So, that is why this will let the sun start to fuse heavier elements because of the increase in the energy due to the gravitational collapse in the core, along with fusing hydrogen in a shell wrapped around the core. When this happens, the sun's temperature will increase, and the outer layer of the sun's atmosphere will expand so far out in space that they will engulf Earth. This is the red giant phase. So, this is, you can go through the NASA website also if you want to read more about how the red giant phase will be occur for the sun. So, this is the general understanding. And in last, it will collapse to a white dwarf. Okay. Now, coming to the question 9. So, question 9 and 10 I will do it in together. So, just one thing. Yes, what is it? Yes. Okay. So, here the question is that photons in the sun can be described using Maxwell-Boltzmann distribution due to what? I mean, okay, so due to what we will come into that, but the main point is that photons in the sun can be described using the Maxwell-Boltzmann distribution. And here the question is, which of the following cannot be described using Maxwell-Boltzmann distribution? That means we have to find out the limitation of Maxwell-Boltzmann distribution in the astrophysical object. That I will do using very small theoretical background. So, as I told you that when a star is burning helium at its core, hydrogen at its core, hydrogen burning phase, everything is okay. The star is stable, hydrogen burning will create the energy, and that will sustain, and that don't allow the gravitational collapse to happen. Now, here when the hydrogen is burnt out, totally burnt out, then the temperature is not enough to burn helium, then the gravitational collapse will happen, the temperature will increase of the core, and then the helium burning phase will start. Okay. And this will continue up to iron burning, and at the last the result will be a white dwarf. Okay. Now, so we have to understand the situation inside a white dwarf and inside the star which is burning, that means the sun, the current situation of the sun. Okay. So, Maxwell-Boltzmann distribution is a thermal distribution, and it is valid in the classical regime only. Okay. So, classical regime means when the distance between atoms, so distance between two atoms are greater than de Broglie wavelength. So, if this condition holds, that means classical limit. Okay. And the quantum limit of this thing is distance between the atoms is smaller than the de Broglie wavelength. So, you know the associated de Broglie wavelength of every particle. So, if associated particle, I mean, if the associated wavelength of a particle is lambda, then it can be expressed as h by p, where h by p is equals to 2me. P is the momentum can be written as 2me, where e is the energy. So, h is the Planck constant, m is the mass. So, lambda is related to the mass of the particle. Okay. This is the de Broglie, famous de Broglie wavelength. Now, so I will not go to the detailed calculation of how it has been done, but actually this limit, this classical limit, when the distance between two atoms, here the atoms means the atoms which are taking part in the fusion, is then the de Broglie wavelength, then that is the classical limit. That means Maxwell Boltzmann distribution holds. But here this case MB doesn't hold. Okay. Now, if you calculate the density of a typical white dwarf, it is of the order of 650. I am taking that's why I am giving it this sign. It is not exact. 650 gram per cc. Okay. So this is very high. So the density of a white dwarf, although the radius is very small, but the density is very high, and at this density, this quantum condition generally holds. I mean, if the density is that much, then the distance between the atoms, as it is concentrated and is in a very small volume, so the distance between atoms are less than the de Broglie wavelength associated with the atoms, and in that case the quantum limit dominates. So the Maxwell-Boltzmann distribution doesn't hold. You cannot describe the inner region, I mean inner particle distribution of the white dwarf by the Maxwell-Boltzmann distribution. But for a sun, the density, this can be calculated using the theory, but I cannot do it right now in the class because it requires much understanding of the astrophysics and quantum mechanics. So for sun, it is 150 gram per cc. Okay, so you can see this is 650 gram, this is 150 gram, at least 4 times smaller than the density of a typical white dwarf, 4 times. So this density is not high enough, and in this limit, in this 150 gram per cc limit, this upper condition generally holds. The distance between the atoms is greater than the de Broglie wavelength. So that means we are in the classical limit, and Maxwell-Boltzmann distribution holds well here. So the main part is the transition between classical to quantum. Whenever you are just going in the quantum regime, then the Maxwell-Boltzmann distribution will not be sufficient, I mean will not be valid. So that is the main background of this question, that protons in the sun can be described using Maxwell-Boltzmann distribution because it is in the classical limit till now. So when the sun will be in the white dwarf phase, then this Maxwell-Boltzmann will not be valid, and that means the density is low comparing to the density of white dwarf, and the temperature is high enough. Okay. So high temperature and low particle density. This law is actually with respect to quantum regime, that's why it is low particle density. So B is the answer. And similarly, the number 10 question is which of the following cannot be described using Maxwell-Boltzmann distribution. That means which object is in the quantum regime, that cannot be, and I told you that white dwarfs are in this regime and it cannot be explained by the Maxwell-Boltzmann distribution. Okay. So that's why I take these two questions together, and it was the answer. So it was the first assignments, and I have some time, so quickly I will go through the it was the second assignment, and in the first class I have not gone through question by question of the first assignment, so I will quickly go through that in this class. So till now, anyone have any questions, they can ask, whether in chat or by unmuting. Okay, so this was the assignment 1. This which are coming, this is assignment 1. So the first question of assignment 1 was, red giant have mass tens of times that of sun. They have as I told you many times, go to that figure, go to the HZ diagram. So these are the supergiant, red giant. Okay. So many types of giants are there depending on the mass. So subgiant, giant, supergiant, whatever may be, whatever it be, but it is above the main sequence. This is the main sequence. And similarly, the white dwarf, which I have also calculated at first, that is below the main sequence. So that is the, you have to remember the, I mean, if you understand, you can remember the what are the location of supergiants and dwarfs in this main sequence. That is the question related to yes. So red giants have mass, greater mass, and they have higher luminosity, higher luminosity than sun. And white dwarfs are smaller than the sun in size, and they have lower luminosity. Okay. Now, the temperature associated with the universal cosmic microwave background, I have told you in the first class that this is the CMB if it is intensity. Yes. Okay. Okay. So in the sorry. Hmm. Okay. So can you who is it? I mean, can it? Okay, so can you do one thing? Just, I mean, I was not in India, that's why I could not register for that class, and I don't know the actual assignment. So can you just send me the assignments in to my mail so that I can go through that? So just mail it in this. So I thought that the assignments will be same, because in the previous course which I have taken in classical mechanics, those are the same assignments. Okay. So that's why I thought it is the same. Just send me right now. You have 2 or 3 assignments, right? Okay. Anyway, that we will not discuss the assignments before the due date. So we have been asked to do it after the due date. So just send me the 3 assignments, and I will go through those just in this email, and I will try if I can find a way to register or get the current assignments. Okay. I mean, is those questions are very different from what is given, what I have done today? Yeah. Okay. 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 No problem. I mean, there is no harm in doing extra questions, but I will do all those questions also. You just send me those. Okay. Yeah. Okay. So this was the temperature 2.7 K. Okay. Now this was another question where you have to calculate the distance. Here this I have also give you the theoretical background of how to calculate this, but I will do the calculation here. So Z, which is the redshift is delta lambda by lambda, which can be written as V by C also, if your V is, provided your V is very less than C, velocity of the object. So uh, delta lambda by lambda means lambda you observed by lambda emitted by lambda emitted. Okay. Now lambda observed is given 4002 minus lambda emitted 3934 divided by 3934. Lambda emitted means the rest frame lambda, okay, which is shown in the laboratory. So this will give you that 68 by 3934, that is 0.017. Okay, now you got delta lambda by lambda equals to 0.017. That means your V by C is also 0.017, which will give you V is 0.017 times C, where C is the speed of light. And from Hubble's law, V is hd, where h is the Hubble constant, and d is the distance. Okay, so V equals to hd, that means your d is V by h, and V you have already calculated 0.017 C by h. Now just put the values. 0.017 C is actually 3 into 10 to the power 8 meter per second, divided by h is given 70 kilometer per second per megaparsec. So we will convert that kilometer to meter. 70, so that is meter per second per megaparsec cube. And what is this megaparsec unit of length? That I have discussed in the previous class. You can go through that. Now if you calculate, it will be like 72.85 megaparsec, that is 73 megaparsec roughly. So this is the distance of that particular object, which is emitting light at 3934 angstrom, but we are, due to this redshift, we are measuring it at 4002 angstrom. So that is 73 MPC. Oh, it is given that in MPC. So megaparsec. Now this is the fourth question. Now 2.7. Yes. Yes. Okay. So have you gone through the age? Age is given 70. Okay. Okay. Like what can you say that? Okay. So I don't know. As far as I have done, I don't think there is any mistake. But just once go through this calculation, it is possible that I have done some mistake here. Okay. Okay. Then maybe they have used 67, which is the old value of the Hubble constant, as you are saying. Maybe. Okay, so whenever you are giving this type of question, I mean the paper setter must mention what value of age we should take, because there is a limit, a range of age values, right? So that should be given, I think. Yeah, that's I am telling that it should be mentioned. Otherwise, a range of age is there, and you can take any of the values. So I don't know exactly what value they will take for this particular thing, but I cannot comment on that. Yeah. So I think, as you are the other students are telling, the 75 would be the right answer, because it is near to 73, not 65. That will be much lesser. Maybe you can just go through. Okay, so this was another question from the theory, that which meteorite played a major role. That is I think Carboniferous chondrite. And which of the following is true for isotopic abundance of elements? That is, even A isotopes are more abundant than odd A. This is the stability of the nucleus coming from different types of models which has been suggested. Now, which follows the correct abundance? The maximum is hydrogen, then it is helium. So first find where hydrogen and helium. So hydrogen is 92 for everything. Helium is 7.1 here, 7.1 here. So yeah, so okay, this options are not right. Only this and this may be right. Now coming to oxygen it is 0.1%, and then carbon. I think this is the correct answer, but yes, this must be the correct answer, that hydrogen greater than helium, greater than oxygen, greater than carbon, which is valid here. Okay, here it is carbon is greater than oxygen, which is not right. So this is not right. Okay, so this is the answer. Now this I have also discussed in the previous class, that cosmic ray are the main reason of projection of lithium, beryllium and boron, because a cosmic ray, which is very high energy particle, when it is moving through space, it will interact with the particles which are from ISM. So this is a cosmic ray particles, and it will interact with the ISM particles. ISM particles mean interstellar medium particles. So there are particles in between stars, that is called the ISM, and that particle, and by doing various type of nuclear reaction, it will give lithium, beryllium and boron. So this is the main projection system of lithium, beryllium and boron. This is cosmic ray spallation. Okay, and which one of the following is true for HR diagram? Stars are distributed uniformly. No. About 20% of the stars are on main sequence. No, it is 80 to 90%. All the stars are either on the main sequence or below it. All the stars are mainly, yes, either or below it, because on the larger side it will be the, no, it can be go on the upper side also, because if the mass is very high, then it can go. So all the stars no, it is similarly, it is also wrong. Red giants are above main sequence, it is correct, and white dwarfs are below main sequence, it is correct. So I think this is the correct option. Red giants are below main sequence, no. White dwarfs are no. So this is your correct answer. The red giants are above the main sequence and white dwarfs are below the main sequence. And stars can be in the main sequence as well as slightly upper of the main sequence and slightly lower of the main sequence. Not every stars are on the main sequence itself. So that's why these two options are correct, not right. And this also I have told you that CMB is coming from all over the universe, and it is very isotopic. So the anisotropy is less I mean 1 in part of 1000. Okay, so this was the, I mean past assignment according to me. Okay, so this was the thing. Now one thing I will do at last, that I told you that, so any of you just mail me your 3 assignments at that email ID. Okay, then I will go through it. So yeah, now at the beginning I have told you that apparent magnitude and absolute magnitude. Coming back to that part, absolute magnitude. Okay, so I will do just one small, I mean mathematical problem. I will say I will try to calculate how much brighter is the sun compared to the moon. That I will do just. Okay. So sun's brightness compared to moon. So m1 is equals to minus 2.5. This will be done by apparent magnitude itself, no problem. F1 by F1. Okay, so remember 1 I will use for moon, the lower mass, and 2 otherwise I have to write moon and sun every time. That's why I have done that. So m1 is that is for moon, and m2 that is for sun. F1 are and F2 are the corresponding flux. So m1 minus m2 will be 2.5 log of F2 by F1. Okay, yes. Now okay, so let us call this delta m. So delta m is actually m1 minus m2. That means delta m is actually magnitude of moon, I mean magnitude of moon minus magnitude of sun. That is your m according to my convention. Okay. So Now if I convert this equation, that means 10 to the power delta m by 2.5, that is actually f2 by f1. Okay, that means f2 by f1 is equals to 10 to the power 0.4 times delta m. Okay. Okay. Now we have the data of magnitude, apparent magnitude of m sun and m moon. So for moon it is minus 12.74 and for sun it is minus 26.832. Okay. Now we will just put that f2 by f1 equals to 10 to the power 0.4. Delta m was m1, that means minus 12.74 minus m2 means 26.83. I'll write it as 83. 2 is not needed. Okay, so that means 10 to the power 0.4 times 14.09 and it will give you as 432513. Okay, so f2 was for sun, right? F sun by f moon is 432513. That means our sun is 4 into 10 to the power 5 times roughly brighter than the moon, which can be calculated using the magnitude system. So that's why the magnitude system is important for the astrophysics, and I thought that I will discuss this particular thing at last. Now if you have any question you can ask, no problem. Right. Yeah. Yes. No, actually you have found that q value, and if you want to find the q value per nucleon, you have to divide it by the total number of nucleon of the parent atom. I think you are talking about binding energy. Generally we calculate binding energy per nucleon, not the q value. Yeah, so binding energy is quite defined. So in binding energy, these two, suppose I am considering fission, that will create a much larger atom. So if it has Z1, Z2, then it will be Z1 plus Z2, or I should write it as nucleon, because proton and neutron both are nucleon. Now here from the mass defect you will calculate what will be the binding energy, right? And that binding energy will be divided by the A1 plus A2, that will give you the binding energy per nucleon. Is it making sense? Yeah. And generally we plot, when you will find a binding energy plot, you generally will see it is plotted as a function of per nucleon, I think. That plot where you can find that iron is the most stable thing. So the x-axis, I don't know, let me just go through binding. Okay. Yeah. Okay. Okay, so which assignment was it? The third. Okay, so I didn't know that the assignments are different. That is a big shocking news for me. Just one of you just send me the assignment. I am again writing my email ID. I will go through the problems in the next class if possible. Okay. Yeah. Okay, so any other questions? I think what I have told you is quite understandable. Okay, now let me see if there is any other thing I want to discuss. Yes, I have discussed this also. Then 71. Okay. 3. Yes. Yes. Okay. Just give me a minute. Okay, no, fine. I have completed everything what I wanted to tell. So, if there is no other question, then I think we can end the session here. And just remember, please send me the assignments. So, thank you. So, I think I am seeing 6 to 8 students here. So, can you tell briefly, I mean, what course you have done? I mean, in which year or in which degree you are right now? So, Aditya, can you tell me? Okay. Integrated MSc. Okay. That means you are in undergraduate right now. Okay, okay, okay. Then Raja Shekhar, can you tell? I mean, so that I can understand the picture. I think he is not here. So Godhuli Pal. Okay. Okay. Oh. Okay. Which university? Okay. Where is it? I don't know. I okay. 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 Fine. So Sanghavi, can you tell? Some of the students are just attending, I think. So Sujata K. Oh yeah, yeah. Yes, sir. Yes. Good evening. Okay. Periyar University means Kerala, right? Okay. Tamil Nadu, sorry. Okay, Tamil Nadu. So you are in which year? Second year BSc. Okay. Then Sujatha. Not here. Ten Mozi, can you tell? Oh, so there are a lot of second year students. Okay. And where? Okay, okay, same. I see. Okay. So, is there any, I mean, astrophysics course in your universities? I mean, I am asking to everyone who are here. Okay, okay. Third year of BSc. Okay. And Priyan A. I think he is not here. And I cannot see others' names, so they can tell from where they are and which class or year they are. These 6 7 names I can see actually. Okay. I think here yeah, I can see. So Sudarshani Bedi, is he or she here? I don't know. Raja Shekhar. Okay, no problem. Okay, fine. Okay, so we will end here today, no problem. Just send me the assignments. I am telling again and again so that I can go through it. Yes, yes. Uh, okay, so I also right now cannot say it because it is a very specific term and I have to go through it. If I say it in the next class, will that be okay? Right now, I don't have any idea of her. Okay, okay. I don't have any idea right now actually. Okay, I will go through it. Sure. Yeah, no problem. Okay, so okay, then we will end here. So thank you very much for joining, and we will meet next week same time 6 p.m. Okay? Thank you. Yeah, thank you. Good night. Yeah.